Okay. Okay. Hope it's recording something. So let's move to the last part. So we have understood how it works. Okay. We have the name nodes. We have the blocks that are spread on the cluster, and then the system is scalable because if we add a server, this provides what? Storage for the data nodes and provides computation capabilities. And it's easy to recover. We have an automatic recover of failures. Okay, that's the basic idea. Then let's have a look on how things work at runtime. Okay, this is an example of a TeraSort benchmark. So here you're sorting. Actually, here it's not 1 terabyte, but it's just 8 gigs. Okay. And you have blocks here are of 64 megabytes. So Hadoop early days, the blocks were 64 megabytes. Today, people use 128 megabytes. So this means that's good not to save your your document, your Word document, because you allocate at least nowadays 128 megabytes for every file, because at least you write a file in a block. And actually, you are replicating this 3 times, right? So it's for big data. It's not for a few kilobytes files, things, okay? So here, we have 8 gigs with the blocks of 64 megabytes. So we have 64 input splits to process, okay? 64 input splits. And then here, you see what's going on. You have the maps, okay? Then here in red, you have the so-called copy shuffle phase, where you are what you are doing is what? You finish the map, you see here. You are finishing the maps. You are writing the data on your local disks, okay? Then you are transferring the intermediate results to the node where the reducer are running, okay? That's what we are doing, okay? So this is the red part. So again, this was a TeraSort implementation. So what you were doing is a kind of merge sort that was implemented there. The maps were ordering the data according to their local data that they have in the local input splits. And then, so you have some partial ordering that you send to the reducer that provides the merge of this data, right? And then you store the data. That's how this is built. You see here, you have also 64 nodes, slots in the MapReduce terminology. So a slot is a CPU devoted for running a task, okay? Then you start the process. You have a local sort because imagine the point is the following: you don't have a single process working on a single key. Okay, the same process can process multiple keys. So imagine that I'm sending to a reducer the data for the A and the B, so these are mixed. They will be processed by the same reducer node. So at the reducer side, you have an initial sort where you sort first the A and then the B. Okay, is this clear? Pay attention because you are lost. And finally, you run the reducer, and then you have so the reduce stage is the one in black here. Okay, and then the computation is finished. Okay, so here you are lucky. You exactly need 60 maps to process your input data. You have a 64 cores slots available. Then you process. You see here, the maps finish in a single wave. You have just one round of maps. You send the data, you process the data, you finish. Here, I was not that lucky. Here I have just 16, I think, slots for the map. And since I have to process 64 input splits, okay, I can work at most on 16 cores in parallel, okay. So you see here that we need 4 ways to complete the processing of the maps, okay. So that's the way it works. You see, when the first round, the first wave of maps has finished, you already start the copy shuffle, okay? But only when the very last map finishes, the reducer starts. And then again, you have multiple, I mean, you're processing, you have more capacity here for the reducers, and then you see, at the very end, you reach the end of the computation. I mean, here you see, you have here we are using less resources, but the execution of this sorting on these 8 gigs double also almost in time. Here before you had just you did the sort in less than 1 minute, and then you double this time because the maps took more waves. Okay. So 2 important things to focus our attention in these 2 plots. The first thing is, there are 2 things that we don't like in the framework. The first one, we have to survive. The things work like this even in Spark, so we go this way. The other things that we don't like, I mean, has been improved in the next version of Hadoop. I mean, this was Hadoop in its very first version, and we have today we have 2.7.3, I think. Yeah, I mean, in the next slides I will tell you how it is evolving. Okay. So, what's the first? Even in these slides, let's see if you have a good eye on these problems. What do you don't like here in this slide? You can have a +1. Let's see if you can see this. We are in a parallel system, okay? And switch to English in a way that also Diana can listen to you.
The lower side of the graph gets underutilized.
Good. Send me an email. Very good. The point is, here we have overall 128 cores. We statically allocated 64 cores for the maps, 64 cores for the reducers. But you see here that while the map is running, the other part is idle. So the utilization here is 50%. So I'm running really, I have a very large cluster, but half of the cluster is not used. Okay, you don't like this. That's very bad. Very good, guy. Good. But you see here, this is less evident here, but you have this is I mean, it's not just a matter of how many resources we have devoted. Here, you don't have in any case. Here you see that the reducer are already running because you have the copy shuffle. You're transferring the data, and while the data transfer, your process is still advancing the computation with that. Here, I mean, the two both are working, right? One is focusing on the data transfer, the other is going on with the computation, but at the very end, you see that the utilization of this cluster, because of this static allocation of the slots for the maps and reducers, the utilization is never 100%. You are wasting resources, okay? So this has been improved with the new frameworks, with the evolution of Hadoop, okay? The other things that we have to survive, I mean, this is something that is characteristic also in Spark, is related to the fact I told you a few minutes before that the reduce stage can start only when the very last map has finished its work, okay? So the point here is until the very last map hasn't finished, I cannot start the computation. okay? And that's also bad. Why? Because in a real world, the map never finish in sync. If they finish in sync, you are happy. But, and this was a very relevant problem in MapReduce, you have the so-called straggler problem. The straggler is the one that comes late. Okay? There are many reasons why you can be late. Because, for example, you have a lot of access to the disk, you are competing to access the disk, or you are competing to access the switch in your rack. Okay? So that's why some maps can be late. And the point is, in this parallel system, that's the issue in this parallel system. The performance are determined by the very last one. Okay. Here you block the computation of the reducer, and here you don't have the final results until the very last reducer has finished its computation. Okay. So you see the performance are already always suffering because of the very last one. Okay. Again, we have to survive with this. In Spark, this straggler problem is less evident because while here you see a map takes seconds. Okay. In Spark, unless for the stage of the data loads that, of course, you are accessing some disks, so you have the time of the disks. If you are reading 1 terabyte of data, you are still reading, even in Spark, 1 terabyte of data. That's no point. But in the other stages, the tasks are, if your cluster is configured properly, the task lasts around 100 milliseconds. So if you have even 100% variability in 100 milliseconds, you are not delaying too much your computation. In MapReduce, if you have the same variability, I mean, and I'm working with 30 seconds waves, I'm delaying by 30 seconds. I'm not delaying by 100 milliseconds. Okay, so this was a problem in this problem was more evident in MapReduce because of how the things were built. Okay. Other question? Any question? No. Okay. This shows that I like, I think, Iron Man, right? Let's see the evolution. I mean, here, this was a Hadoop 1.0. I think we had the first two release, I don't know, 2012 probably. And actually in Hadoop you have two versions. One is unstable and experimental, and it is updated every 4 months, more or less. One is stable, which is the one that is adopted by companies, and the stable version is updated every 6 months, more or less. So what they did in Hadoop 2.7 and something. The last release was last December, I think, more or less. They rechanged the architecture of the framework. So before we have the job master, okay, that was managing everything, okay. Nowadays we don't have the job master anymore, but this has been split into multiple components, okay. Which are these multiple components? These are the resource manager, okay, and the application masters. Why actually? I told you before, the job tracker was a single node, a single point of failure in the system, but also, since the clusters are shared by multiple users, this becomes a bottleneck. Imagine that I'm submitting, imagine that Filippo orchestrates the work among you, and I'm sending all of the jobs to Filippo, okay? Earlier or later, it will be overloaded. I mean, you will be idle probably because he's still coping with the request I'm sending to him. So it's not going to have a single node processing the job submissions in a cluster that is shared. And it doesn't only, his job is not just to receive my request, but his job is also, I mean, to monitor what you are doing, because if Francesco becomes idle and he has some jobs in the queue, we'll send immediately jobs to Francesco, for example. So he's also monitoring. So you understand, in a large cluster, shared cluster, the work of the job tracker becomes idle. Okay, he's doing a lot of work. I mean, so it's not good. It's better to split the responsibility. Okay, the responsibility are the responsibility of the monitor and the resources, the responsibility of the job management and the job scheduling. So the new framework, how is built? We have the resource manager. The resource manager actually is a global scheduler that decides how to split the nodes in the cluster among the running jobs. Okay. Then we have the application master, and we have an application master for every application running. Okay. And the goal of the application master knows what are the data, which are the nodes where it can run the tasks, okay, and he will schedule the execution of the task on the nodes that he can use, okay. And finally, the node manager is the one that is providing really the resources. So the node manager stores the data again and then provides the additional resources and manage also the life cycle of the containers, because now the tasks are dynamically allocated to containers to cope with the issue of the 50% utilization of the cluster. We don't devote the resources statically, but we dynamically allocate the slots to running tasks, and these are allocated into containers. Okay. So how this works, and then the final, okay, the last final point is, before we had this strict, we say, structure of map and reduce stage. Okay. Now, with the new framework, we can run on directed acyclic graphs. Okay. And this is has a huge implication in the performance. So let's focus on this picture here. I told you before, MapReduce just provide me map and stage. Every computation is built with these two functions. If I have a complex computation, or imagine that I have to process two different input data sets, okay, I have to split. Really, I can build a complex application by relying on multiple jobs. Okay, these are the first job, then this is the second job. Here I have a single job, and this final one will, merge the results of the two analyses, for example, the two data processing. Okay. The point here is, here I told you the reducer store the final results to HDFS. What does it mean? That data, before I can proceed in the computation, okay, I have to replicate the intermediate results at least 3 times, we said, okay? So here, you have a lot of I.O. A lot of I.O., since there are at least 2 orders of magnitude between the time you need to run in the CPU and the time you access the disk, okay? A lot of I.O. means that jobs are slow, okay? In the new evolution, actually, you see that here, you have the concept, this guy here, this is the initial map, these are the map and reduce of Hadoop 1, okay? And they are the same here. They are the map and the reduce, they are similar really to the same task, the same function that we had in Hadoop 1. This guy here is a new guy, and this guy is an intermediate reducer, okay? And the reducer gets directly the data from the previous stages, okay, without storing to the HDFS, without replicating 3 times the intermediate data. So you understand that here, the computation, just because you are eliminating all of the so-called I.O. barriers, you have some synchronization barriers because of the I.O., okay? You are removing this, the same version, the same code, the same analysis, it's much faster because you are eliminating the intermediate replication of data to HDFS. Finally, and I think we can stop here today, this is the issue of the dynamic resource allocation. Here, see, I don't know, here we have, I believe, 20 slots, okay? These are really what you get from the monitoring system of Hadoop. Here you see, for example, here I'm running map 40, here I'm running map 32, and so on. But you see, if I have, let's say, 20 cores, I'm devoting these 20 cores to the maps. Okay? When the map starts finalizing their job, I allocate the reducers and I dynamically allocate the map and the reducer to my cluster according to what I need. I don't split statically as before. So in this way, you increase a lot the utilization of your clusters. That's very, very relevant. You don't have resources idle, so you pay for resources. I would complain if on average 50% of my resources are idle. Okay? So that's the new innovation. That's most the innovation in Hadoop 2.7 and something. For what concerns HDFS, HDFS still survives in almost its initial form. The only thing, the main innovation, let's say, that they bring in HDFS, so to the distributed file system, is related to the fact that the framework is aware of the technology. So at the beginning, we have just mechanical disks. Nowadays, we have SSDs. They are much faster than the disks. So if I have some data that I need to access more frequently, okay, than other, I can say when I store to the HDFS, please provide me SSDs if available in a way that the computation of this data will be faster. Okay? And then you can also say, okay, I can have some caching, so some intermediate results, instead of storing to the disks or to the SSDs that are slower, in any case, keeping memory in a way that I can be faster if I need to access this data again. Okay? So these are the most important innovation from the performance perspective on HDFS. Okay? HDFS, in this way, is still using Spark. So while we move to different framework, to different engine for the parallel execution of jobs, for the data storage, we are still relying on the same ideas of 2000s, more or less, with this updated technology. Okay? Good. Really, that's all for today. Hope you didn't suffer too much. This was the technology part. I try to really drink the most because I don't know if you like the metadata of a file system, but I mean, these are important concepts. Okay? The beam was set off. See you tomorrow.
Aspetta che salvo la registrazione, altrimenti qualunque cosa io dica potrà essere usato contro di te.